Today we talk about parameter estimation. There are two methods to do that. The first one is maximum likelihood estimation. It will choose the parameter that provides the largest value of the likelihood function. It's intuitive appeal, which means it's easy to understand, and it's perform well when sample is large. So there are some general steps. The first one is to specify the likelihood function in terms of the parameters to be estimated. Then we create the function. Assume that we have a random variable sample x1 to xn from a distribution. The likelihood function of the observation is a random sample psi n's in the formula as below. For example, for the Bernoulli with n1s of 1s and n2 of 0, we will have the following formula. For continuous random variable, the probability density function, and for the discrete, it is the probability mass function. And note that the likelihood function follows the IID samples identically and identically distributed and joint distribution. Then we estimate the process by finding the value that makes the observed data most likely. There are three ways to do that: graphically, which means we rely on the plot; calculus, which means we find the critical point; and numerically, which means we try a lot of numerical value using Python's SciPy, for instance. For calculus, we derive the likelihood function by calculating the derivative of the likelihood function. For example, is above. One way to do the maximum likelihood estimation easily is doing the log likelihood. Since the original likelihood function is a product, it is difficult to solve sometimes. So we turn it into sum by log the likelihood function. In practice, often it's more convenient to cope with the log likelihood rather than the likelihood itself. Log likelihood is also more likely to be concave, which means it only have one maximum or one minimum point. So the normal distribution has a very special formula for maximum likelihood. From the likelihood function of the normal distribution random variables, we can directly calculate the optimal mean and variance. Also, for if we have multiple random variables, for example, one dependent variable y and multiple independent variable x, we can directly calculate the most optimal mean and variance of the joint distribution based only on x and y. Although it is very convenient and easy to understand, there are also some limitations. The first one is the non-existence of maximum likelihood estimation. For example, when we applying that method to some variance of uniform distribution, because there is no likelihood function, we cannot calculate the optimal value of the parameters. The second one is the non-uniqueness of the maximum likelihood estimation. For example, when applying that to a mixture of two distributions, we will have multiple critical points. Therefore, it will be difficult to find out which one is the most optimal one. And the value of the parameters that maximize the probability distribution function of the data is the value that assign the highest probability to seeing the observed data, not necessarily the value of the parameter that appears to be the most likely given the data. The second method is the maximum ex posterior. If we consider the probability distribution over the model parameters, we can look at the posterior distribution that updates the prior Having observed some data using the likelihood, the formula is on the screen, where we have the distribution of parameter and the distribution of x through all possible parameters. However, it is usually very difficult to calculate the distribution of x, which represent the relative likelihood of data under the model for all possible parameter values. However, since we mostly interested in the shape of the posterior data rather than the actual values, this can be ignored and we can simply look at how the posterior change as not the posterior, the prior change as the distribution of the parameters changes. One note is that if the prior is uniform or flat, the maximum likelihood inference and the maximum a posterior inference are equivalent. One application of this method is the naive Bayes. To do this, we can use the prior probability of the output of a data point being to a class and the probability of a data point given the class to calculate the classification problem to assign the output to some unseen data.